Physics by R. W. James, M.A. Cantov, B.Sc. Lund, Capt. R.E. Owing to the continued drift of the ship with the ice, the program of physical observations originally made out had to be considerably modified. It had been intended to set up recording magnetic instruments at the base and to take a continuous series of records throughout the whole period of residence there. Absolute measurements of the Earth's horizontal magnetic force, of the dip and declination being taken at frequent intervals for purposes of calibration. With the ice continually drifting and the possibility of the floe cracking at any time, it proved impracticable to set up the recording instruments, and the magnetic observations were confined to a series of absolute measurements taken whenever opportunity occurred. These measurements, owing to the drift of the ship, extend over a considerable distance and give a chain of values along a line stretching roughly from 77 degrees south lat to 69 degrees south lat. This is not the place to give the actual results. It is quite enough to state that, as might have been expected from the position of the magnetic pole, the values obtained correspond to a comparatively low magnetic latitude, the value of the dip ranging from 63 degrees to 68 degrees. So far as possible, continuous records of the electric potential gradient in the atmosphere were taken, a form of quadrant electrometer with a boom and ink recorder made by the Cambridge Scientific Instrument Company being employed. Here again, the somewhat peculiar conditions made work difficult, as the instrument was very susceptible to small changes of level, such as occurred from time to time owing to the pressure of the ice on the ship. An ionium collector, for which the radioactive material was kindly supplied by Mr. F. H. Glue, was used. The chief difficulty to contend with was the constant formation of thick deposits of rime, which either grew over the insulation and spoiled it, or covered up the collector so that it could no longer act. Nevertheless, a considerable number of good records were obtained, which have not yet been properly worked out. Conditions during the expedition were very favorable for observations on the physical properties and natural history of sea ice, and a considerable number of results were obtained, which are, however, discussed elsewhere, mention of them being made here since they really come under the heading of physics. In addition to these main lines of work, many observations of a miscellaneous character were made, including those on the occurrence and nature of perhelia, or mock suns, which were very common and generally finely developed, and observations of the auroral displays, which were few and rather poor owing to the comparatively low magnetic latitude. Since most of the observations made are of little value without a knowledge of the place where they were made, and since a very complete set of soundings were also taken, the daily determination of the ship's position was a matter of some importance. The drift of the ship throws considerable light on at least one geographical problem, that of the existence of Morel Land. The remainder of this appendix will therefore be devoted to a discussion of the methods used to determine the positions of the ship from day to day. The latitude and longitude were determined astronomically every day when the sun or stars were visible, the position thus determined serving as the fixed points between which the position on days when the sky was overcast could be interpolated by the process known as dead reckoning, that is to say, by estimating the speed and course of the ship, taking into account the various causes affecting it. The sky was often overcast for several days at a stretch, and it was worthwhile to take a certain amount of care in the matter. Captain Worsley constructed an apparatus which gave a good idea of the direction of drift at any time. This consisted of an iron rod which passed through an iron tube, frozen vertically into the ice, into the water below. At the lower end of the rod in the water was a vane. The rod being free to turn, the vane took up the direction of the current, the direction being shown by an indicator attached to the top of the rod. The direction shown depended, of course, on the drift of the ice relative to the water, and did not take into account any actual current which may have been carrying the ice with it. But the true current seems never to have been large, and the direction of the vane probably gave fairly accurately the direction of the drift of the ice. No exact idea of the rate of drift could be obtained from the apparatus, although one could get an estimate of it by displacing the vane from its position of rest and noticing how quickly it returned to it, the speed of return being greater the more rapid the drift. Another means of estimating the speed and direction of the drift was from the trend of the wire when a sounding was being taken. The rate and direction of drift appeared to depend almost entirely on the wind velocity and direction at the time. If any true current effect existed, it is not obvious from a rough comparison of the drift with the prevailing wind, but a closer investigation of the figures may show some outstanding effect due to current. The drift was always to the left of the actual wind direction. This effect is due to the rotation of the Earth, a corresponding deviation to the right of the wind direction, being noted by Nansen during the drift of the Fram. A change in the direction of the wind was often preceded by some hours by a change in the reading of the drift vane. This is no doubt due to the ice to windward being set in motion, the resulting disturbance traveling through the ice more rapidly than the approaching wind. Cf. Scientific Results of Norwegian North Polar Expedition, 1893-96, Vol. 3, p. 357. For the astronomical observations, either the sextant or a theodolite was used. The theodolite employed was a light 3 seconds vernier instrument by Carey Porter, intended for sledging work. This instrument was fairly satisfactory, although possibly rigidity had been sacrificed to lightness to rather too great an extent. Another point which appears worth mentioning is the following. The foot screws were of brass. The tribrach, into which they fitted, was made of aluminium for the sake of lightness. The two metals have a different coefficient of expansion, and while the feet fitted the tribrach at ordinary temperatures, they were quite loose at temperatures in the region of 20 degrees Fahrenheit below zero. In any instrument designed for use at low temperatures, care should be taken that parts which have to fit together are made of the same material. For determining the position in drifting pack ice, the theodolite proved to be a more generally useful instrument than the sextant. The ice flows are quite steady in really thick pack ice, and the theodolite can be set up and leveled as well as on dry land. The observations, both for latitude and longitude, consist in measuring altitude of the sun or of a star. The chief uncertainty in this measurement is that introduced by the refraction of light by the air. At very low temperatures, the correction to be applied on this account is uncertain, and, if possible, observations should always be made in pairs with a north star and a south star for a latitude, and an east star and a west star for a longitude. The refraction error will then usually mean out. This error affects observations both with the theodolite and the sextant, but in the case of the sextant, another cause of error occurs. In using the sextant, the angle between the heavenly body and the visible horizon is measured directly. Even in dense pack ice, if the observations are taken from the deck of the ship or from a hummock or a low berg, the apparent horizon is usually sharp enough for the purpose. In very cold weather, however, and particularly if there are open leads and pools between the observer and the horizon, there is frequently a great deal of mirage, and the visible horizon may be miraged up several minutes. This will reduce the altitude observed, and corrections on this account are practically impossible to apply. This error may be counterbalanced to some extent by pairing observations as described above, but it by no means follows that the mirage effect will be the same in the two directions. Then again, during the summer months, no stars will be visible, and observations for latitude will have to depend on a single noon sight of the sun. If the sun is visible at midnight, its altitude will be too low for accurate observations, and in any case, atmospheric conditions will be quite different from those prevailing at noon. In the Antarctic, therefore, conditions are peculiarly difficult for getting really accurate observations, and it is necessary to reduce the probability of error in a single observation as much as possible. When possible, observations of the altitude of a star or of the sun should be taken with the theodolite, since the altitude is referred to the spirit level of the instrument and is independent of any apparent horizon. During the drift of the Endurance, both means of observation were generally employed. A comparison of the results showed an agreement between sextant and theodolite within the errors of the instrument if the temperature was above about 20 degrees Fahrenheit. At lower temperatures, there were frequently discrepancies which could generally be attributed to the mirage effects described above. As the Endurance was carried by the ice drift well to the west of the Weddell Sea, towards the position of the supposed Morel land, the accurate determination of longitude became a matter of moment in view of the controversy as to the existence of this land. During a long voyage, latitude can always be determined with about the same accuracy, the accuracy merely depending on the closeness with which altitudes can be measured. In the case of longitude, matters are rather different. The usual method employed consists in the determination of the local time by astronomical observations and the comparison of this time with Greenwich time, as shown by the ship's chronometer, an accurate knowledge of the errors and rate of the chronometer being required. During the voyage of the Endurance, about 15 months elapsed, during which no check on the chronometers could be obtained by the observation of known land, and had no other check been applied, there would have been the probability of large errors in the longitudes. For the purpose of checking the chronometers, a number of observations of occultations were observed during the winter of 1915. An occultation is really the eclipse of a star by the moon. A number of such eclipses occur monthly and are tabulated in the Nautical Almanac. From the data given there, it is possible to compute the Greenwich time at which the phenomenon ought to occur for an observer situated at any place on the Earth, provided his position is known within a few miles, which will always be the case. The time of disappearance of the star by the chronometer to be corrected is noted. The actual Greenwich time of the occurrence is calculated, and the error of the chronometer is thus determined. With ordinary care, the chronometer error can be determined in this way to within a few seconds, which is accurate enough for purposes of navigation. The principal difficulties of this method lie in the fact that comparatively few occultations occur, and those which do occur are usually of stars of the 5th magnitude or lower. In the Antarctic, conditions for observing occultation are rather favorable during the winter, since 5th magnitude stars can be seen with a small telescope at any time during the 24 hours if the sky is clear, and the moon is also often above the horizon for a large fraction of the time. In the summer, however, the method is quite impossible, since, for some months, stars are not to be seen. No chronometer check could be applied until June 1915. On June 24th, a series of 4 occultations were observed, and the results of the observations showed an error in longitude of a whole degree. In July, August, and September, further occultations were observed, and a fairly reliable rate was worked out for the chronometers and watches. After the crushing of the ship on October 27, 1915, no further occultations were observed, but the calculated rates for the watches were employed, and the longitude deduced, using these rates on March 23, 1916, was only about 10 minutes of arc in error, judging by the observations of Joinville Land made on that day. It is thus fairly certain that no large error can have been made in the determination of the position of the Endurance at any time during the drift, and her course can be taken as known with greater certainty than is usually the case in a voyage of such length.